Hey guys, today I'm going to be doing a quick little demo to demonstrate heat transfer and to talk to you a little bit about specific heat of different substances and how that applies to real world scenarios. This is a pretty simple demo and I'm going to be using these specific heat transfer blocks that you can order from any of various science catalogs like Flynn or whatever. So you have these two different blocks and I'm going to try to describe them to you as best I can. So this one is very light. It is like a composite wood material. You can see there it's kind of porous, smooth on the top, very lightweight. This other one we have here is made of metal. As you can hear, it's a lot heavier, smooth, very dense, again made of some kind of a metal material here. Okay. Now, before I would begin this activity, I would ask students to make some observations on each one of the materials. So they would talk about kind of the things that I just explained to you in those observations. The next thing that I would have them do is put their hand on each one and talk a little bit about what the differences are by way of how they feel temperature-wise. So as you can imagine, because obviously you can't reach out and touch these, the metal one feels colder than the wood composite one. At this point, I would pause and ask students to make some kind of a hypothesis up about if I were to place an ice cube on each one of these, which one they think that the ice cube would melt on faster. So if you are using this as a lab activity, go ahead and pause here and have your students hypothesize which one, the wood one that feels warmer or the metal one that feels cooler, which one an ice cube would melt faster on. So I'm going to actually put an ice cube on each one here. I'm just going to set this down for a second and open the bag up. All right, so in here I have little ice cubes. Shout out to the nurse's office for providing me with these. All right, and I'm gonna try to take two pieces that are about equal here and place it on each side. Oh. This one fell apart, but I mean, the differences here are gonna be pretty similar anyway, but. So as time is going on here, the ring is supposed to keep the water in, but this desk is slanted. So as you can see, the ice is melting a lot faster on the metal one. These haven't even started melting yet, really, over here. And I'm about to have some water in my lap here in a second. Okay, so that's pretty much done. So there you have it. Now, at this point, I would maybe have my students talking about why they think this happens. So at this point, another thing that I would have my students do is I would have them feel, because in most schools, kids have these sort of desks here where you've got the wood top and then, part of the side here is made with metal, right? So what I might also have them do is put their hand on the desk and then put their other hand on a part of the metal of the desk and try to compare those temperatures. And usually students will say that the top of the desk feels warmer than the metal parts of the desk. Now, the key thing here to remember, which a lot of people probably don't realize, is that if you're in a room, everything in that room is the same room temperature, except us. Humans, we have, body temperature regulation, like homeostasis, about 98.6 degrees. We have like a little furnace, right? But everything else in the room is the same temperature. So like these two blocks, even though the metal one felt cooler, well, now it definitely feels cooler, and we'll talk about that in a second. Even though it felt cooler than the wooden one, they're the same temperature. Same thing, the top of the desk and the sides of the desk are the same temperature. And so why then does metal feel cooler? We all know that metal conducts heat really well, right? Metal gets hot really quickly. We learn this if we've ever left like a spoon or a fork in like a pot or a frying pan for like a little too long and then went to grab it and it's really hot, right? Metal gets hot really quickly. Metal also cools off really quickly. And the idea of things heating up and cooling off is sort of like a perception depending on the object that's in contact with it. Is it warmer or cooler? So for example, as a human, right, I am about 98.6 degrees. And when I touch metal that's at room temperature, I am a lot warmer than it. So it feels cool to me because the heat from my body is leaving, going into the metal. See, that's the thing. You can't absorb coldness. You can only lose heat. So when something feels cold to us, that means that we are warmer than it and we are giving our heat to it. And we perceive that as being cold. So when you go outside on a cold day, you're feeling cold because you're losing heat. If I touch metal and it feels warm to me, that means that it is warmer than my, 98.6, and it is giving heat to me. So why then, when I touch the metal, if I'm losing heat to both of these objects, why does the metal feel colder? So it feels colder because it's taking my heat at a faster rate than the composite would. So just like metal heats up really quickly, it absorbs heat energy really quickly, it can lose it really quickly as well. And so in this case, it's actually taking my heat away faster than the composite wood is. If metal is hot compared to something else, it'll also give me heat a lot faster. So in this case, what happened was the ice was colder than both. So the metal gave heat to the ice faster than the wood did. And what's interesting is if you feel them now, the metal feels really cold because it lost a lot of its heat, giving it to the ice as it melted the ice. Same thing with the desk here. The top feels warmer than the metal part because the metal is taking my heat away faster. So what does this mean for specific heat? Specific heat is a numbered value. It can range anywhere from like 0 to, I don't know, probably the highest one I'm aware of is something like water, which is 4.18. Metals tend to be like somewhere between 0.2 and 0.6, so they're much lower. So specific heat, the lower your specific heat is, the faster you transfer energy. So you warm up really quickly, you cool off really quickly. You ever seen a video where there's like a blacksmith forging a sword and it's red hot and they douse it in water and it cools off really quickly? Or you might have done that before too. You might have cooled off a pot or a pan really quickly under some cold water, right? Metal cools off really quickly as well, whereas water takes an eternity to heat up and cool off. That's kind of why I don't like going swimming, because pools, lakes, whatever, they never get warm enough for me to ever want to get into them. Water also is really hard to cool off. You have a pot of boiling water, you can throw a lot of ice cubes in there and it's going to bring the temperature down maybe a little bit, but it's just going to melt that ice really quickly without very much effect on the temperature. So at this point, you could start applying this to real world scenarios. So, for example, if you have to stand on two surfaces on a cold day and your hope is to stay a little warmer, would you rather stand on a wood surface or a metal surface? I have this great picture of these little birds standing on a fence, and there's a wire, and then there's a wood post, and there's a bird on the post, and there's a bird on the wire, and I say which bird has warmer feet. You could also talk about like why are playgrounds now typically made more out of wood and plastic than metal. There's a lot of implications. You could talk about why coastal areas tend to have a similar temperature year-round compared to places inland. So you can branch this into earth science. There's a lot of different places that you could take this. So hope that this was helpful. If you have any questions or anything, let me know in the comments. I also have a worksheet that goes with this, so if you're interested in that, you can send me a message.